Hi guys, welcome back. In this video we are finding limits of sequences. We're also going to talk about what it means for a sequence to converge or to diverge, and then we're going to look at special cases, a couple of special cases. Sometimes we say a sequence diverges to infinity, and sometimes we say a sequence diverges to negative infinity. So before we get started, I think it's helpful to think about a sequence in a slightly different way for this section, for this topic. Remember we said that a sequence is just an ordered list of numbers, and usually we start with n equals 1, so we get a sub 1, a sub 2, a sub 3, and so on, and we keep going. We go down the list. Well, we could graph this by graphing the set of ordered pairs n a sub n. I did this on the last video, but I didn't talk in detail about how we graph. Basically, you take that integer n, which is where you start, and then whatever value that's here, that number on the list, that's the y value in the ordered pair. So when you graph it, you don't get a continuous function like the functions we're used to. You get a bunch of points in the xy plane. So at n equals 1, you might have a sub 1 is here. And n equals 2, it might be the case that a sub 2 is there. And when n equals 3, it might be the case that a sub 3 is there. And so on. Now, it might happen that after a little while, all of those values start to approach a line. So we might have a line given by y equals L. And it's possible that as n increases, the points or the values that are listed here get closer to this line L. So maybe when n equals 4, a sub 4 looks like that. When n equals 5, a sub 4 or a sub 5 looks like that. A sub 6 is there. A sub 7 is there. And it's okay if we cross the line. Maybe a sub 8 is on the other side, but maybe we're just getting very close to that line. In that case, we say that this sequence a sub n has a limit of L, and we write it this way. The limit as n goes to infinity of a sub n equals L. The limits that we're going to be computing in this section are very similar to limits at infinity that you studied in Calculus 1. We're just thinking about it a little differently. In Calculus 1, we had functions of x, and as x went to infinity, we had this continuous curve, nice smooth curve, and we wanted to know what happened to the y values on that function. We're looking for y values here as well, at least in these ordered pairs. We're thinking of this as an xy pair. Again, n is our independent variable, and a sub n is our dependent variable. But instead of something that's continuous, I'm just looking at a bunch of points. I'm looking at the values of those points and seeing if they get close to L. So here's the formal definition of the limit as n goes to infinity of a sub n. We say the limit as n goes to infinity of a sub n equals L means for every epsilon greater than 0, there exists an m such that if n is greater than m, so n is the index, so if we're far enough down this list, then the absolute value of a sub n minus L is less than epsilon. And you might say, how does that have anything to do with this idea up here? Now let's draw another picture. Let's say the limit is L again. And this is the line y equals L plus epsilon. And this is the line y equals L minus epsilon. And I'm going to make my ends not so far apart this time. Excuse me, the n values on this axis. So I'll just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can get a whole bunch of points. Now, what this says is eventually. Maybe at the beginning, your a sub n's are all over the place. Sometimes they're in between, sometimes they're not. But eventually, maybe after this point, 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe after n equals 9, all of the values are in between these two lines. Maybe it looks like this. I know, it's all a weirdness at the beginning. It looks scattered. Sometimes it looks like statistics. It looks like a scatter plot, right? We don't care what happens at the beginning. What this limit is saying is, after you get past here, n is greater than 9. For all those values, the y values are in between L plus epsilon and L minus epsilon. And you might say, how does that tell you anything about this behavior? Well, this is for every epsilon greater than 0, no matter how small. No matter what epsilon is, even if epsilon is 0.0001, that limit is 5. If I go far enough down on this list, I can get all of the a sub n values within 0.001 units of 5. So between 4.9999 and 5.0001. I hope I listed the right number of 9s and the right number of 0s, but I hope you get the idea. It's as epsilon gets tiny, this is shrinking and shrinking, the y values, or the a sub n values, are going to be in between those two lines. So that's the formal definition. We're not going to use that, but I just wanted you to see it at least once. That's what we mean. As n goes to infinity, a sub n is approaching L, or equals L. The limit of a sub n is equal to L if this is true. Intuitively, we usually use this definition. As n increases without bound, so n gets larger and larger and larger, a sub n gets arbitrarily close to L. So we can make the values of a sub n as close as we want to L, as we want, by letting n get large enough. And when we say as close as we want, you say how close? It's epsilon close. It's within this epsilon interval around L. Okay, so if I want to determine whether a sequence converges or diverges, one way I could do it is to just graph it and then look at it, and then I could try to infer from the graph what the behavior of the function is long term for n going to infinity, or the sequences for a going to infinity. Or I could look at a list of values. I could look at all of the a sub n's on the list and see if they seem to be approaching something. But if I want to prove it, I'm going to have to use the limit laws and the limit properties and techniques that we learned in Calculus 1 for limits at infinity. So we're going to use algebraic techniques for evaluating this limit from Calculus 1. Okay, so keep that in mind. Also, I wanted to define convergence and divergence. So we say, and this is just a term, we say that the sequence a sub n converges to L if the limit as n goes to infinity of a sub n equals L, and L has to be finite. That can't be plus or minus infinity over there. Now, if the limit happens to be infinity or negative infinity, those are special cases. In those cases, we say that a sub n diverges to infinity or it diverges to L. In general, we say a sub n diverges if the limit as n goes to infinity of a sub n does not exist for whatever reason. It might not exist because the limit is infinite, might not exist because you're doing something like taking the sign of n and it oscillates forever. So that's our definitions of divergence and convergence of sequences. A sub n diverges if the limit does not exist. A sub n converges to L if the limit exists. And of course, the L is a finite number, so that this definition actually makes sense. Okay, so let's look at a few examples. On this one, I want to determine if the sequence converges or diverges. There are lots of different ways I could do this. I could make a list of values and see what seems to happen. I could graph the function and see what seems to happen. Both of those are going to allow me to estimate or infer what the limit's supposed to be. Or if I want to find the exact value of the limit, if it exists, to see if the sequence converges, I just use the Calculus 1 techniques for evaluating limits. So let's do this one first. I have the limit as n goes to infinity of 10 over n plus 2. N is very large. So if n is 1,000,000, this is 10 over 1,000,000 plus 2. 10 over something very large is a fraction that's very small. And if n becomes 1,000,000,000,000, this gets even smaller. If I add more zeros to that denominator, this gets even smaller. So as n gets larger and larger, the fraction gets smaller and smaller, and the limit is 0. So we would say this sequence converges to 0. Now that's the algebraic approach. And that's the approach we tend to use in this class because that proves things. All right. Now we can also take a numerical approach. Now the numerical approach is a good approach for your intuition. It is not proof. So you can use the numerical approach to figure out what the answer probably is, but it's not going to prove anything, and it's not going to count as justification for your answer when I ask you to prove things in this class. So let's find a sub 1, a sub 2, a sub 3, and then maybe a sub 100, a sub 101, a sub 102. I like to do some calculations of terms for large n because I think it tells me what the trends are. It tells me how this function tends to behave. So I'm replacing n with a 1. So I have 10 over 1 plus 2, so that's 10 over 3. Replacing n with a 2, 10 over 4. We could simplify that, of course. Replacing n with a 3, 10 over 5. And so on. Let's replace n with 100. So I have 10 over 102. Let's replace n with 101. Well, that's 10 over 103. Then with 103 we get 10 over, or 102 we get 10 over 104. And you keep going. Now I know that these simplify. That is 3 and a third. So it's approximately 3.3. And then 10 over 4, what's that simplify to? Yep, 2.5. 10 divided by 5 is 2, and you keep going. Now 10 over 102 is really close to 1/10. It's not quite 1/10. It's actually 5 over 51. But that decimal approximation is 0.098 approximately. And then 10 over 103 does not simplify at all. But that's 0.097. And then 10 over 104 simplifies to 5 over 52. I'm using my calculator over here on this side to get these decimal approximations. And we've got this. Now you might think from this list, that maybe this limit is 0.1 or something like that. But notice that they keep getting smaller. It's not clear from the list, from the numerical approach, but they do seem to be getting smaller. I've got 3 1/3, 2 1/2, 2. Eventually I'm getting these little tiny decimals that are close to 1/10. To really see, I need to plug in a sub 1000, plug in n equals 1000, n equals 1,000,000, and see what happens. So the numerical approach tells me it's probably 0, but this list is also misleading. I might think it's something like 1/10 when it turns out that it's not. So it appears that from this list that maybe the limit is 0, maybe it's 1/10, but we saw from the algebraic approach, as n goes to infinity, 10 over something really large, something really small, we get 0. Let's look at this same limit geometrically. At n equals 1, we get 3.3. n equals 2, we get 2.5. n equals 3, we get 2. n equals 4, so I'm going to have 10 over 6. It's about 1.6. n equals 5, 10 over 7. So I'm getting about 1.4. n equals 6, 10 over 8, 1.25. Should be up there. Equals 7, 10 over 9, 1.1. 8, we get 10 over 10, which is 1. And it's decreasing. It's sort of decreasing slowly, but it's slowly decreasing. And you just keep going. Eventually you plug in 100 and you get 10 over 102, which gave us this 0.98. And you're still not there yet. But as you continue, you go on and on and on and on. And I don't want to go on and on and on and on. But if I did go on and on and on and on, all these values are getting very, very close to 0. Y equals 0. So that means the limit is 0. And if the limit is 0, we say that the sequence converges to 0. So the limit exists, it's 0, so the sequence converges to 0. Now let's look at this guy. Now you might be tempted to just write down this, the limit as n goes to infinity of -1 to the n plus 1. And I hope that that bothers you. I hope it bothers you because this is a large number plus 1. If that large number plus 1 is even, I've got -1 to an even power, it's going to be 1. If that large number plus 1 is odd, I've got -1 to an odd power, it's going to be -1. So I can't just say -1 to a very large power is 0 or -1 to a very large power has one value, because it doesn't. Half the time this is going to be 1, the other half the time it's going to be -1. If you don't believe me, let's look at a numerical approach. So a sub 1 is -1 to the 1 plus 1. -1 squared is 1. A sub 2 is -1 to the 2 plus 1. -1 cubed is -1. A sub 3 is -1 to the 3 plus 1, -1 to the 4th, which is 1. A sub 4 is -1 to the 4 plus 1, -1 to the 5th, it's 1. So every other integer, I've got an even, then an odd, even, then an odd, even, then an odd. -1 to an even power is going to be 1. -1 to an odd power is going to be -1. So if I draw these in my list, I'm going to have 1, or write these on my list, excuse me, 1, -1, 1, -1, 1, -1. And then if I sketch it, when n equals 1, y equals 1. When n equals 2, y equals -1. When n equals 3, y equals 1. When n equals 4, y equals negative 1. N equals 5, 1, then negative 1, then 1, then negative 1, and it continues. You might be saying, does it have two limits? And that's tempting, because it looks like it does have two limits. Half the time it has a limit of 1. The other half the time it has a limit of negative 1. But this is just like a function in Calculus 1. You're not allowed to have two limits. As n goes to infinity, half the time we approach 1 and half the time we approach negative 1. You only get one limit. You don't get to have two limits. It's not allowed. If you've got two, these are called subsequences. They're sequences within the sequence. They all stay in the same order and you look at them in the same order that they came in. You got one subsequence where they're all 1 and one subsequence where they're all negative 1. If you've got two subsequences with different limits, the limit does not exist. So this limit does not exist. And we say that a sub n diverges. And let me write that down. I'm going to call it a theorem. It's not a theorem in our textbook. They mention it, but they don't call it a theorem. But it's an important fact. There we go. If a sequence has two subsequences that converge to different limits, the original sequence diverges. Because you can't have two limits, you only get one. Okay, so keep that in mind. All right, now let's look at some other examples. A couple of simple examples. Now here, if I want to evaluate the limit, I could evaluate this numerically or graphically. Probably be easier with a calculator or a computer because that's it's just arithmetic. We can do it, but I'd rather not waste my time doing arithmetic, not in this class. I'd rather think about big ideas, how concepts are connected. So here I have the limit as n goes to infinity of 4n squared over n squared plus 2n plus 3. Now, if this was an x, this would be an infinity over infinity indeterminate form. The same is true here. Now, if you want to use L'Hopital's rule, you can, but you can't use these n's. You've got to change to x, and we're going to talk about that in a different video. I'm going to give you another way for evaluating this limit that does not require L'Hopital's rule. There are going to be some other problems in the next video where we have to use L'Hopital's rule, so we'll review that then. But for this one, if you've got a polynomial divided by a polynomial, the easiest way to get rid of that zero or that infinity over infinity indeterminate form is to divide the numerator and denominator by the highest power of n in the denominator. So the highest power of n in this denominator is n squared. We're going to divide by n squared there, and we're going to divide by n squared up here. Now watch this. Remember how this works. If you've got a polynomial with multiple terms, you divide each term by the n squared. In the numerator, n squared over n squared, that cancels, and we just get the 4. N squared over n squared is 1. 2n over n squared. One of those n's will reduce, and we'll just have a 2 over n. And then the last one is 3 over n squared. As n goes to infinity, this guy goes to 0, and this guy goes to 0, and so we get a limit of 4. So what does that mean? Well, one thing that it means is the sequence converges to 4. You might say, well, what does that mean? Well, I'd have to plot some points to figure it out, but I know that y equals 4 looks like this. And maybe we've got some interesting behavior. I don't know if it goes up or down or how it behaves. I don't know. Maybe it looks like this. Who knows? But I know that my sequence eventually approaches this line, y equals 4. Okay. So we can get rid of infinity over infinity indeterminate forms that involve polynomials by dividing by the highest power of n in the numerator and denominator. Then this one, well, that is an arithmetic sequence. We talked about that in the last video. As n increases, I think we get negative infinity, don't we? Negative 2 times a large number is a large negative number. Adding 6 to it doesn't do much, so we get negative infinity. So this is a sequence. It's pretty simple. And we say this diverges to negative infinity. And let's see what it looks like. When n equals 1, we get 4. When n equals 2, 6 minus 2 times 2, 6 minus 4 is 2. When n equals 3, 6 minus 2 times 3 is 0. When n equals 4, I think we go down 2 and over 1, we get that. Go down 2 and over 1 again, you get that. Down 2 and over 1. And so you see this linear relationship. It's not a line, but it's sort of behaving like a line. All those points line up on the line y equals 6 minus 2x. But it's not a line, it's a sequence. It's just the graph is just this scatter plot points. Got a sub n over here on this axis and the n value on that axis. But we see, when we say that this diverges to negative infinity, we just mean those points are going off to negative infinity. Looks like at a constant rate of negative 2 units per unit. And just keep going, just going down and down and down. And that's it. Okay. Now in the next video, we're going to look at more limits of sequences, and we're going to look at some sequence theorems. So that's just your introduction. Now, let's see, what did we look at in this video? We talked about the graph of a sequence and what that looks like. Trying to find my notes for that first beginning of the video. Oh, I can't find them. I think I put them in the recycling pile. But we did talk about the graph of a sequence and what that looks like. And we talked about what it means for a sequence to diverge or converge. If the limit exists, and that limit is a number, the sequence converges to that number. It means that when you graph it, the points get closer and closer to that line. If the sequence diverges, that just means that the limit doesn't exist. Now, it might not exist in a special way. Like this one doesn't exist in a special way. It goes off to negative infinity. Sometimes people will say if the sequence diverges to negative infinity, the sequence decreases without bound. That just means it just keeps decreasing and decreasing and decreasing. Here's one that increases without bound. Let's say you've got 1/5 n squared. Well, as n goes to infinity, obviously a large number squared is a large number. Multiplying by 1/5 makes it a fifth as large, but it's still large. So we get infinity. So this sequence, diverges to positive infinity, and we say this one, this sequence, increases without bound. Oops, there you go. So when n equals 1, we get 1/5. When n equals 2, 4/5. N equals 3, 9/5, which is nearly 2. N equals 4, 16/5, just a little bit more than 3. N equals 5, 5 squared over 5, which is 5. And so we're seeing that parabola, that y equals 1/5 x squared parabola. We don't get the whole parabola, we only get a few points on the parabola, actually infinitely many points. But as n goes to infinity, those values of our sequence are increasing without bound, they're going up. On this one, the values on our sequence were decreasing without bound, they're going down. Now you always read your graph from left to right. So from left to right, this is going down, from left to right, this one's going up. So that's what we meant by those terms, and we'll do some more advanced examples of finding limits of sequences and look at some sequence theorems in the next video.